Levi asking about slide number 3. Wow, that's a lot for me to read. You spent a long time on the picture and size timescales. I know that you are working on charge carriers cooling, but do you need to spend 2-4 minutes on explaining the methodology behind material science?
No, ideally it would be like 30 seconds, but yeah, that's kind of what I hoped for those first 2 slides.
Okay, and I think it makes the presentation oriented to broader audience, especially this time and size scale comparison for multi-scale modeling would be interesting to those who do molecular dynamics as main activity. Levi's question for slide number 4. How does this relate to your work? You are not doing nuclear chemistry. Why spend 2-3 or more minutes on topics that seem unrelated to your work?
Again, same answer as previous. I guess the main motivation is like we talk to, I don't know, people not even sort of in material science, and it's hard to describe. So it's useful to, I don't know, make a story as how like material science is done in practice. And everybody has an idea of the Manhattan Project.
Maybe it's also related to an attempt to apply for a job at Los Alamos and give them credit.
Yeah, it never hurts.
Okay. Yvonne asking about slide number 7. Keep the color scheme consistent.
Yeah, if I made the figure, I would, but yeah, it's from, yeah, ideally I would like to make the color scheme consistent, but then I would just have to make the figure myself.
Slide number 10 by Levi. You need to make sure the arrows and animations work if you are going to use animations.
Yes.
Okay, was quite a quick answer. Slide number 10, question from Amir. The order of the animations in the slides show is not sorted.
I think it's the same comment as Levi's.
Yes, yeah, that was the same.
Slide number 13, question by Levi. What is multiple MEG?
But I said multiple MEG. That was a mistake, and I put in 2 M's. There should only be 1.
Okay. Questions from me to unknown slide, probably one of the next slide with the electronic structure and DFT. So it's maybe 5 slides later. Or green box in the center. I think it is 19. Yeah. Oh, okay. You already erased. There were 2 indices. Yeah. Okay. Yeah. No questions. Light to matter interaction. It's also one of the subsequent slides after that. Yeah, probably 21. You're mentioning independent orbital approximation, but you're not mentioning that dipole interaction is also an approximation. And one of your committee, or even 2 or 3 committee members can come after you on that. Just mention that dipole interaction between light and matter is an approximation, and only the first term in more general expansion.
Mhm.
Slide number 3, Electron-Phonon Interaction. The non-adiabatic coupling is introduced like as a given equation without connection to like basics, molecular Schrodinger equation, Born-Oppenheimer approximation, and same as for light to matter interaction. This is only a first term in more general expression. And at least one of the committee members likes more if the derivative is over positions rather than time. So either place more details here or prepare a backup slide on source of this non-adiabatic coupling and other forms to write it down. Like this time derivative can be replaced by first derivative of a space. In general expression, it includes both first and second derivatives. Okay. Levi is asking about electronic structure slide. I think we should flip back to number 19. And Levi, please correct me if I'm navigating wrong. So, it's a quote from Levi. I know you have to show the equations, but your explanation was poor for anyone who doesn't know what the equations mean. Would you color code the equations in the flow chart to connect these two? The flow chart is easier to understand compared to equations for non-computational people. So maybe after we are done with the discussion, you attempt to address some parts of the suggestions.
I guess I'll just say that I think my description got backward because I put my equations in the wrong order, so I was kind of stumbling over myself. So that's why they might not have made sense. I guess, yeah, my equations shown in the green box should have been in the same order as the algorithm.
So the questions from our audience today is just an indication of where the audience on your formal defense can stop following, and it can be addressed either by changing visual form or just maybe spending 30 seconds more and indicating connection, like pointing to this and that box. But it's just a way to present, right?
Mm-hmm.
Levi is making comment on slide number 25. Why is your method better? You said populations, but is that all the benefits? If populations is it, I'm sure SE can get population.
I guess I don't know if I ever said our method was better. I never really did a comparison between surface hopping and Redfield, but I guess in practice they're equivalent. It's just a way to describe formalism. I mean, the real difference comes into the approximations that are made between something like Redfield and surface hopping, and that usually has to do with coherences.
Okay, and formally, Levi is telling a comparison between Schrödinger equation and von Neumann. So can you address this question? Like, does Schrödinger equation provide changes in populations? This is a good exam question.
Well, I mean, yeah, so from the Schrödinger equation within a specific basis, you can get changes in the amplitudes which correspond to a specific, I don't know, eigenstate. I guess not eigenstate, but a specific part of the expansion.
Okay, so there is a constructive and destructive interference for change in some other observables, but does Schrödinger equation shows transition between eigenstates?
I guess not by itself.
Mm-hmm. So if it would, then we wouldn't need other methods. So it's fine to defend Redfield against Schrödinger. There were two questions from me, but by mistake I typed it not to everyone, but to Lola by some reason. Slide 26. Provocative question. Subscripts V and C are not defined, or maybe you define them later after I type the question. Why Redfield tensor in one notation has 4 indices, R with subscripts ij, kl, and in one equation, and in other equation it has 2 subscripts, R sub vc.
On slide 26.
Yes, exactly. Like on the top line, you show RIIJJ equals RVV. No, the very top left.
Oh, okay.
And why pairs of indices are the same? You do not need to answer right now, but just meditate and prepare to answer on it if someone asks.
Right. Well, yeah, it's not it's notation which V is valence, C is conduction. So it's not a rigorous notation, but it's helpful for describing what's shown in the figure.
Okay, next provocative question. Can this approach monitor coherence and decoherence in principle? Is it practiced in what is presented?
And what's presented, no, but in principle, yes.
Okay. So if I would answer my own question, I would say that Redfield tensor has 4 indices, so it's one needs 4-dimensional space to present it, but one looks only on a slice of this object that controls changes in population, and changes in coherence are left for the future. Therefore, instead of 4 indices, we set up pairs of indices being the same, and we focus only on change in population. Although methodology in general shows more shows additional processes.
Mm-hmm. I do have a backup slide to combat those questions.
Yes.
So like C is if it's a very large band gap, so you have long-lived coherences. But for energy gaps from thermal energy, the coherences decay very quickly. So we can get by with neglecting them.
Okay, it's great. You are ready. Slides 30, 31. Question for myself. 30. It's where you show geometry of, yes. Do you balance charge of all anions and cations in the model? Do they result in a total zero charge?
Yeah, no. So that's one approximation.
But can you justify it? Not for me, but for the audience and for possible questions from audience.
Well, justified in what sense?
If all anions and cations in the model do not give total zero charge, does it mean that even if you are not introducing Fullerenes, you are dealing with charged system? Is it okay? Is it bring any errors? On experiment, most models are neutral. So do you assume some counter ions floating, or just why it is needed? Why charge cannot be made neutral?
Well, I guess in practice, charge could be made neutral, but then you'd have to compensate that by defects on the surface.
Yep.
Trade-off between.
Then the system will lose symmetry.
Right.
Okay.
And in terms of like methodology and details, there is an accounting for background charge, which helps make the calculations stable.
Okay. Slide number 34. One parenthesis is missed in the bottom equation.
Yes.
Excellent. Yeah, here. Same slide question from Amir. Oh, same question. I was just 10 seconds earlier. Okay. A long question from Levi. Whew. For Redfield dynamics, is this your work or others? If it is published before, I would take most of the details out because you spent 25% of your time on describing the method. Most of the details you say I couldn't reproduce because it seems disjointed. I know that each slide was connected, but for a person who is not familiar with your methods or Redfield would get lost. It might be good to have another flow chart which would stay throughout your discussion on Redfield. This would connect what you are talking to things people outside your group would understand. I know it is painful, but if you have time, it would be helpful for answering questions. So what is your reaction?
Well, I guess by design, I anticipated spending a fourth of my time on methods. So that's actually good to hear. I guess like the two other, I don't know, committee members, one's an experimental physicist and then the other's a heavy theorist. Because I'm sure they'd be interested in knowing some of the theory to follow along with the studies that I do later on. And I know Eric has a particular, like you'd probably want to see something about particle in a box, which might seem a little excessive, but something to try to just spend 1 minute on. And I guess in terms of the red field, I'm not sure what's to get lost at. I guess the main summary is that from couplings, we can produce state-to-state rates. Then we choose initial conditions to propagate dynamics. I guess I could put that into a flow chart somewhere along the way.
And let me try to answer a question Levi is asked to you as I would feel to answer myself. So I didn't design red field method. I didn't design spinor approach to DFT. And even if I didn't, if I wasn't first who combined them together, I mean, Aaron, I was the first who applied this method to this material. And to understand the strong qualitative and quantitative consequences of this modeling of the results, we need to refresh the details of methodology. Maybe something like that would satisfy Levi.
Yeah, because if I went the other approach, I didn't specify, or if I didn't like highlight spin orbit coupling or non-radiative dynamics, it's kind of hard to I don't highlight the sellable parts of the research.
Mm-hmm.
Maybe I just have to make those aspects clear.
Okay. So next question is from myself on slide 34. So for the committee members without physics background, which differential equation was solved in this demonstration, in this slide?
Like order?
No,
the Schrodinger.
Yes. And you can just add it and tell that this Hamiltonian and this potential is plugged into Schrodinger equation, and then we provide these solutions. Because some of the audience may fall asleep and then wake up. And just I would type H phi equals E phi. And then tell here is H, here is phi, and here are how they are represented. Mm-hmm. Yep. Levi is asking, and he's not on the meeting, so we cannot ask if you satisfy his question. But he's asking next question about the same slide. How does this, about slide 34, how does this relate to your work? If people, something is wrong with grammar. If people want to learn effective mass approximation, they can read a book. You spend 5 minutes to show SH and SE. Is this worth the time during your defense? Are you able to explain EMA? I think EMA means effective mass approximation, but how would you answer if this question would be asked during formal defense?
I guess I'm pretty sure effective mass isn't included in these slides. It's just particle in the box. I don't know if it's exactly effective mass, but I guess I include this because I know Eric would want something about relating particle in a box to quantum dots. And I could probably gloss over details, and if somebody was unclear, they could ask a question during the defense. So yeah, maybe I should just spend less time going point by point through the observables.
So,
Just comparison.
I'm absolutely confident it is very appropriate slide here, but just how to answer such question, like what is the connection of the slide to the rest of the work? Which benefits does it give to understanding of the other achievements and considerations?
I guess just showing there's a similarity in orbitals between a crude model and something like DFT, and then there are similar trends in energies.
Okay, so it provides a framework to interpret computational data.
Mm-hmm.
And maybe sets some definitions.
Yes.
But consider how to incorporate this words like this in your talk, just to avoid questions like the one Levi asked. So we turn back to some very basic background theory to set up framework and definitions to interpret what will follow on the next slide. So slide 35, and I think David Graupner and myself are asking the same question. So David formulates it this way. Slide 35 might be good to add a visual of the envelope function rather than trace it. And my formulation, yes, exactly, perfect. Yeah, thank you. And I formulated, consider to add handmade envelope function as Kia did 2 weeks ago. Yes. Okay, yep. That's great. Thank you, David, for having a unity of mind with myself. Slide number 39, question from Levi. Why not put this with your methodology? You are only adding SOC, question mark. This should be easy to add with the methodology and would allow people to better understand where the orbitals go from Kohn-Sham orbitals to spinors.
I mean, I could put it with earlier in the methodology, but I guess the reasoning to put it with each, or put it with this first study, is that I guess that's one of the novelties of the study itself, is it's one of the first to not just do spin orbit coupling calculations, but to do dynamics.
Okay, then you can just verbally tell, then let me remind you once again a key part of the methodology that will be shown on the next slide. Just guide audience as spoon feeding kids.
I guess that's what I tried to do with this equation. Large spin orbit coupling with the confinement gives slower cooling.
Slide number 42. Question from Yulun. Why to show Redfield tensors figures again?
Yeah, that might be redundant, and I guess I can either delete it or just say that's what the Redfield tensor looks for this model, and then just move on quickly.
And question from myself on the same slide, why the bars have different height? I know that you explained it in the papers and on previous meetings several times, but just be ready to tell it now or later why this alternative pattern of tall and not tall. Is it like spin conservation in one and spin flipping in the other?
I guess in some sense, I guess each energy level is twice degenerate. So energy levels that have very small gaps will have high rates. And so then each alternating bar is just the degenerate levels. And they're only on the diagonal, so it's...
Oh, so it's transition for, between two degenerate level, basically transition to itself.
Right.
Between its like twin brother.
Yeah, in some sense, they don't really contribute that much to the dynamics. It's just going back and forth.
But it's very interesting. I think some of the audience and committee members may appreciate this analysis. Okay, slide number 43. Question from Levi. What does it mean for a bright transition? Did you show the oscillator strength formula?
I did in my method, but I should, I have to go through and like copy and paste some of the equations to relevant slides.
Okay. Next question from Levi. Question to Aaron. From Levi. A quote. When I was getting ready for my defense, Dmitry asked me what I did in my research and what others did. I will also ask you that question because I do not know which equations you implemented in your code and what others did. After you start talking about your research, are all the equations shown developed for your research?
Well, I guess I haven't. I guess I don't spend a lot of time describing what others have done specifically. I spent some time describing what's like topics that people are researching, but not necessarily how they go about researching those problems.
Although Levi gives reference to me, I think it is not as important, but potentially some of the committee members may demand it. Just request you to declare what is your personal contribution to this research. Although it is self-evident by you being a first author, you may get ready to formalize like which part of the methodology was borrowed, which part you contributed yourself, which one you used for the first time for a given system. Even maybe for some small amount of novelty, be sure to be able to confidently tell that like it's my novel idea, and maybe no one will require it, but just in case, get ready.
Oh, he meant like co-authors.
Co-authors, it still considers yours. Not among co-authors, but among other world. You and your team.
Yes. Okay. Okay. Yeah. I thought by others, I thought he was talking about competitors, and not like.
No,
You're saying, though, Dimitri.
pardon?
I understand what you're saying.
Okay. And maybe it will not be needed, but if you think about it ahead, this questions like this will not surprise you. Slide number 49. Question from Levi. What does omega and tau mean in this image?
Omega is for transition frequency, and tau is relaxation time.
Okay, maybe just type it right here to avoid possible questions.
Yeah.
Okay, great. Slide 50. Question from Levi. Not sure if your other slides have this, but images/animations would be very helpful for the add electron or add hole. So it looks like Levi wants visual.
Mm-hmm. Yeah, I think. Yeah, I can think of some figures I would probably help from
Okay.
having those little descriptors.
Slide number 56. Definition of ST. If it is surface trap, maybe just type it because it can be not clear for majority of audience. Like ST equals surface trap. Excellent, thank you. Slides 56, 57. Question for myself: why repopulating of the surface trap is needed? Would brightness of the transition disappear without repopulation? Is it a prerequisite for polarization of the model? You are muted. Oh no, you're not. Probably you just were not speaking.
Can you? What do you mean by repopulating?
On the bottom density of states, you have the red filling of the peak corresponding to ST, and the void, the absence of population at the SH. Why this promotion of the population from SH to ST is needed? Would the results be the same or different if you do not perform this promotion of population? Is it something critical and most important in the whole work, or it is just a little illustration?
Oh, it's very important. So I guess the comparison would be the panel on the top. So it's the same defect, but without any charge in the conduction band. So without having the charge in the conduction band, you don't see the surface trap state. And I attribute that to nuclear reorganization, or so like a polaron.
Okay.
And I should mention that both of the models, so it's the defect is created and then both are optimized.
Mm-hmm.
So this top figure is optimized on the ground state energy surface. And this bottom panel is optimized on the lowest excited state surface.
Okay. Slide number 58. What is gamma? How does it relate to R sub VC and R sub CV?
So they are equal.
So just declare or type it. Good. And in the bottom equation, I think minuses are not needed for, yeah, here, remove them. It's a typo. Minuses in front of RCC and RVB. Okay, yeah, thank you. Next question from Yulun. And it doesn't indicate the slide. How to evaluate these results? Do you have experimental data to compare with?
On my summary slide, I mentioned a couple of experimental observations that have been reported that these calculations could potentially give insight to. So Stokes shift and then stretching of the photoluminescence decay.
Okay, but you do not provide the experimental and computed data on the same panel.
Right.
For some reason?
I guess I could put it in the summary slide.
But think about if it is possible, then do it. If it is not possible, be ready to explain why it's you prefer not to do it. Like it's not mandatory, just to avoid critical questions during the formal defense. Next question by Levi. How does your damping of occupation relate to experiment? Can you say that your damping function is physical or arbitrary? Could these methods be used for other materials, or would you have to feed to experimental data? It's an easy question.
So the dampening comes straight from the, I guess, Redfield calculations. So it's, yeah, so there's no need to, yeah, so there's no parameters to it. It's just what we compute based on, as a function of temperature.
And this method was already used a couple of weeks ago when you presented results on metal organic complexes. And at this time, Levi was not asking the question, right? It was already used in the data, just was not focusing attention and not showing the equations. Okay. Slides 59, 60. Question for myself. Is a fading of the bright stripes a main is a main demonstration, main consequence of added recombination decay?
Yes.
Maybe it would be reasonable to emphasize this significance. And maybe some keyword. I would say fading, but maybe you can find something better.
Oh. You think that would work, or just?
Mm-hmm. Yep. Yeah, great. Next question from Levi. Photoluminescence quantum yield of 95%. Is that in a range, or are you also including energy below 1 electron volt?
Yeah, the quantum yield calculation doesn't come from the integrated luminescence. So it's a separate calculation. Yeah, it is a good question because I mean, you can measure the area like under the integrated curves, but then the hard thing is to like.
It will give the quantum yield more than 100%, right?
Yeah. It's hard to define input power.
I was trying to answer to Levi to this question in the following words. Emission below 1 electron volt doesn't change number of carriers. It is an optical way of cascading from singlet number n to singlet number n minus 1 excitations. And quantum yield is computed only by recombination back to S sub 0.
Mm-hmm.
Okay. Next question from Levi. What is the difference between table of contents and figure on slide 60?
Oh, those are. I guess this is linear scale shown in the contents.
Okay.
And these are log. So that's why the.
Mm-hmm.
Yeah.
Okay, good. Next comment from Levi, great job. And next comment to me, but I see it only one. Levi writes to me, most of my comments are for Aaron to read through. You do not need to read my comments. Sorry, Levi, I already read your comments. Next question from Levi. Did you define MEG?
I think so.
Okay.
2 charge carriers from one excitation, or more, 2 or more carriers from one excitation.
Okay. I think that's it. All questions are done. So please, thanks to everyone who was joining and listening and supporting Aaron either by questions or just by presence. It is a great help, and due to your attendance, it will be a way to improve and present better than possible on the day of defense in 9 days. So please join me in thanking Aaron. once again. I hope the recordings went well, and it will be distributed specifically to Aaron and made available to everyone else to watch it. And formal part of the meeting is done.